everybody. My name is Archana Shrikanta, and I'm the founding engineer of Fargate. I've been with AWS for 8 years. I've been through EC2, ECS, and now Fargate. And I'm joined by owner Phyllis, who is our awesome principal engineer on the Fargate team. And together today, we're going to walk you through the Fargate architecture. We'll tell you all about how it works under the hood and how it's continuing to evolve as we speak. And we hope that at the end of this talk, after you see and understand some of the inner workings, you're able to better reason about the service for your own application use cases. And also that some of the more general design principles that we've used in building Fargate and at AWS in general, we hope that it strikes a chord with you and you're able to take those principles back to your own applications, because we really do believe that the services that we build here at AWS are probably not that different from the types of services and applications that you build on AWS. So hopefully we can share some lessons and learnings there. So with that, let's get started. So the goal of AWS Fargate was very simple and straightforward. We wanted to give our customers a way to run containerized applications on AWS without ever having to provision or scale or manage or interact in any way with virtual machines or the underlying EC2 instances. So a completely container native experience on AWS. And a quick recap of what that container native experience looks like on Fargate. First, you register a task definition. Task definition is just a specification document that tells us about your application containers, the image URI, the amount of CPU memory for your application, et cetera, et cetera. And notice that within a task definition, you can have multiple containers. And what this means under the hood is that we treat all the containers within a task definition as a single unit, and we deploy it onto the same virtual machine, so they're co-located. Then you create a cluster, and note that this isn't a cluster of EC2 instances or VMs, but it's rather just a way for you to group your applications. So some customers use it as a namespacing construct or a permissions boundary, for example. Then you call the RunTask API with the task definition and a cluster, and boom, you have a serverless instantiation of your containerized applications running on Fargate. So as you can see, there were no EC2 instances or VMs involved in this experience. So as we were cooking up this service, once we settled on the overall goal of the service and the customer experience, the ball gets handed down from the product team to the engineering team. And one of the first pieces of documentation that we put down as the Fargate engineering team was a list of design tenets. Now, these are broad, general principles that we put down to help guide the engineering team through the design process and the technical decisions that we had to make along the way, especially when there are hard trade-offs to make. So these are the tenets that we came up with for Fargate, and it's in priority order, so that's important. Priority number 1 is security, always, period. So if we're ever faced with the design choice where this one design is so much better than the other design along all these dimensions and axes, but we just have to make this one small security compromise, we will not do it. We will not even consider that option. And security in the context of Fargate means that the entire hardware and software stack underneath your task is always patched and secured and up to date. And basically, your task, your application is protected from any kind of unauthorized access, either over the network or access to the credentials and permissions that your task may be using, or to the actual data that your task is crunching on. Our second tenet is availability and scalability. And what this means is that we really strive to maintain the uptime of your tasks that are running on Fargate. And not just running tasks, but we also strive to make sure that the service itself is up and available to accept new task launch requests, or stops for that matter, so that you have a reliable way to scale your applications up and down as the need of the hour changes. And then once we have a rock-solid security and availability story, we focus on operational efficiency. With a service like Fargate, we see tens of millions of launches a week, and we're running a huge server fleet underneath all of this to host your tasks. And at that scale, it becomes important for us to constantly identify and eliminate sources of waste in that fleet and constantly improve our resource utilization. And oftentimes, this gets passed back to you customers as price drops. And in fact, we had a major price reduction for Fargate earlier this year. We announced savings plan for Fargate. So this is the tenet, this is the engineering tenet that makes those kinds of improvements possible. So the agenda for today is we'll walk through an introduction of the Fargate architecture, and then we'll walk through each of these tenets to see how they've actually influenced the design. And you'll see that these are not just some things we write down on a piece of paper and then never look at it again, but they're very much living, breathing principles that really are embodied in our designs, and you'll see that. And finally, some of you might have heard all the buzz around Firecracker. It's a new virtualization technology developed at Amazon, and Fargate is actually in the process of adopting Firecracker under the hood. And the reason that we're adopting Firecracker is because we believe that it's really going to help us along these tenets that we talked about. So as we go through each tenet, we'll stop to see how Firecracker is helping on that front. All right, so Fargate architecture. And for the purposes of this presentation, we're going to focus on the RunTask API because that's where all the magic happens. So broadly speaking, the Fargate architecture consists of a control plane and a data plane. The control plane basically is the services that are running the Fargate business logic to orchestrate your task launches. So it's kind of the brains of the system. And the data plane is the huge fleet of servers that run your containers. So it's kind of the muscle, the brawn of the system. And this is the high-level RunTask call flow. So when you call RunTask, it first hits our control plane. We then reach out to the data plane and acquire and reserve server capacity for your task. And then we persist intent in the control plane to launch that task onto that capacity. And then the call returns back to you with the pending task. Asynchronously, the control plane reaches down to the server capacity that was reserved and issues the instructions to launch the containers in your task definition. We bring up the containers in the data plane on the server that was chosen, and then the data plane reports back to the control plane saying the containers are up and running. So now let's take a look at each of those boxes, the control plane and the data plane, in a little bit more depth, starting with the data plane. And remember that this data plane that we're going to talk about here is the pre-Firecracker data plane, so we'll cover the Firecracker-based data plane in a little bit. So data plane, where do your containers run? Surprise, surprise, they run on EC2 instances. Now, these are not EC2 instances that live in your account, so you don't see them, but they are EC2 instances that live in a Fargate account within a Fargate VPC. And one other thing about these instances is that we don't actually launch these instances in the RunTask workflow itself because it would take too long. VMs typically take minutes to boot up, and that's, in most cases, unacceptable for container startup times. So we actually keep a pool of pre-running EC2 instances that are already up and running, and as your task launches come in, we just pick an already running instance and put your task on it. So now let's zoom into one of these EC2 instances and take a look at what the full stack looks like. Starting with the physical server. This is a physical server that's installed in an EC2 data center somewhere. And on that physical server, there's a hypervisor that manages the VM virtualization for EC2. And this portion of the stack, the server and the hypervisor, is all managed by the EC2 team. On top of that lives the EC2 instance. So this is the Fargate instance that we launch using run instances just like you would launch EC2 instances. And within this instance, we run Amazon Linux 2 as our guest OS. And we install a Go agent, the Fargate agent, in there. And the responsibility of the Fargate agent is to communicate with our control plane. And then we have the container runtime, which is Docker in this case, to actually spin up the containers. And this entire portion of the stack within the EC2 instance is managed by the Fargate team. So we patch it, we upgrade it, you don't have to worry about that. And generally, we maintain the full life cycle of this EC2 instance. And above that is our protected asset, which is your task in your containers. Networking-wise, the primary network interface for this EC2 instance at 0 is actually in the Fargate VPC, because the instance was launched in the Fargate VPC. But when this instance gets selected to host a task, we create an elastic network interface, or an ENI, in your VPC, and then we attach it to this instance as a secondary network interface. And any traffic, network traffic that's coming from the Fargate agent, or any of the system components that's between that Fargate task line and the EC2 instance line, is going out through the Fargate ENI through our VPC. But any network traffic that's coming from your applications, including your image pull and logs pushing, is happening through your ENI through your VPC. So that's an introduction to our data plane. So now let's take a look at our control plane. In the spirit of microservices and not building a single giant monolithic service, we actually have a few different control plane services that are each responsible for a distinct piece of the system. Starting with the front-end service. So the front-end service is the entry point service. So the public endpoint that you hit when you call RunTask is hosted by the service. And the service is responsible for performing some pretty standard front-of-door gatekeeping activities. So it enforces IAM authentication, authorization. It enforces all our limits, et cetera. Then we have the cluster manager system. So this is our big backend service. And this is the service that keeps track of your clusters and the tasks that are running in them. And this is the service, the control plane side service, that communicates with the data plane. So this is the other end of that communication channel. And then we have a capacity manager service. And this service is responsible for instances. So it keeps track of both unused available instances in our warm pool and instances that have been checked out and are actually hosting tasks. And on the RunTask workflow, this is the service that's responsible for picking a specific instance for your task. So we have to pick an instance of the right instance type and size based on your task requirements with the latest software installed. So this is the service that does that. And then also, as we use up capacity instances from our warm pool, this is the service that's responsible for replenishing that capacity. So now let's put all of this together and take a look at that call flow one level deeper. So RunTask comes in, hits the front-end service, we perform auth, and we perform limits enforcement. Front-end forwards the call back to the cluster manager service, which keeps state about clusters and tasks. So we will add a record in our database for your new task and mark it as pending. And then the cluster manager system will call out to the capacity system to actually acquire capacity for this task. The capacity manager service will inspect the pool of instances that are available, pick a specific instance, record that instance as now being reserved for this task so we don't have other requests that end up on that same instance, and returns the capacity ID back to the cluster manager service, and that gets recorded in the capacity manager services database against the task, and the call is returned back to you with the pending task. Asynchronously, capacity manager service reaches down to the instance that was selected through that Fargate ENI and activates the Fargate agent. So we keep the Fargate agent kind of in a suspended state when it's in the warm pool because it's not in use. It's at this point that the Fargate agent actually gets activated. The Fargate agent will then register with the cluster management service. The cluster management service is expecting this instance to register, so as soon as it sees that, it actually sends down the task definition and any other information that the agent needs to launch the containers. The agent makes the requisite Docker commands to actually spin up your containers, and then reports the task as running back up to the control plane, at which point we flip state in the control plane. So this is basically it. This is what happens. This is all the magic that happens underneath the hood when you make a RunTask API call. Now, in the next section, we have a little surprise for you. We're going to talk about EKS on Fargate. So how many of you heard the announcement from Andy Jassy on Tuesday? That's right, most of you, I think. So we thought this talk wouldn't be complete if we didn't at least touch upon how we built EKS on Fargate and how EKS fits into this architecture picture. For those of you who missed the announcement, the gist of it is that so far you could use the ECS RunTask API to run serverless tasks on Fargate, and that will continue to be the AWS native API to access Fargate. But now, with this launch, you can actually use the Kubernetes APIs on EKS to run serverless pods on Fargate. So what does the EKS on Fargate architecture look like? And this is just a sneak peek. So we still have a control plane and a data plane, except in this case, the control plane is actually your EKS cluster that's running the Kubernetes control plane underneath the hood. And the data plane, as before, is just a bunch of EC2 instances that are running in a Fargate VPC, and they have the requisite Fargate and Kubernetes agents installed on them. So when you create a pod, it hits the Kubernetes API server, which is a standard component in Kubernetes. And then we've introduced this concept of an EKS Fargate profile. And the profile basically gives us some additional information that we need to launch your pod on Fargate. And one of the things you can specify in the EKS Fargate profile is a set of rules based on namespaces and labels that tell us whether we should route a pod to Fargate or route it to EC2 instances that are running in your account as before. And the reason that we did this is because we didn't want to introduce a new field on the pod itself to tell us that run this pod on Fargate, because then that would mean you'd have to edit all your existing pod specs that you have out there and maintain separate pod specs to run on EC2 versus Fargate. So we wanted a more dynamic way to figure out whether a pod should run on Fargate or EC2. And so what we do is we look at all the profiles that you've registered with EKS, and we look at your incoming pod spec, and if your pod is being launched in a namespace and has the labels that match a Fargate profile, then it gets routed to Fargate. Otherwise, it goes to EC2 instances in your account. And this matching logic is being carried out in a new webhook that we wrote and that we now install in your EKS clusters. And the webhook basically is automatically invoked by the Kubernetes framework every time a pod is created. And the outcome of this webhook is that we basically set the scheduler name on the Fargate to indicate our decision. And this mutated pod spec then gets persisted in etcd as normal. And asynchronously, based on the scheduler name that was set on the pod, it either gets picked up by the default scheduler, in which case it will be scheduled onto your EC2 instances, or it'll get picked up by a new Fargate scheduler that we've written and now also runs in your EKS cluster. And the Fargate scheduler basically owns all the interactions with the Fargate data plane. So it calls out to our data plane to acquire capacity, sends down the pod specs. The agent on the instance will bring up the containers in your pod spec and report it back as running back up to the control plane. So this was kind of a high-level sneak peek into EKS Fargate architecture. This topic can probably use its own under-the-hood talk someday. But for now, let's go back to the ECS Fargate architecture and revisit those tenets to see how that has influenced the design. Now, we switched the order of the tenets a little bit just for presentation purposes. So I'm going to start with availability, and Owner will cover security and resource utilization. So availability. As most of you know, AWS services are offered in a bunch of different geographical regions, and Fargate is no different. So when it comes to availability, the first order of business is making sure that these different regions function as independent failure domains. So minimizing any chance of correlated failures between regions. So how do we do that? So we actually run a separate stack end-to-end across the data plane and control plane for every single region. And these stacks don't talk to each other, they don't know about each other, to the point where even the physical servers underneath the services and the data plane fleet, they actually live in data centers that are local to that geographic region. So if there is some kind of an infrastructure failure in that region, we can be pretty sure that it won't affect the stack in all the other regions. Oh, and also, deployment-wise, software deployment-wise, also we're very careful and deliberate about the cadence with which we push a software change through the regions. So typically we'll start with a single region, deploy it out there, give it a healthy amount of bake time, watch our services and metrics, and make sure everything's healthy before we move on to subsequent regions. And as we deploy to more and more regions with no problems, we gain confidence in the change, and then we can start to speed up the deployment. So next up is availability zones. Availability zones are meant to be basically sub-failure domains within a region. And again, they're designed from the ground up, from the data centers, to make sure that they have independent fault characteristics. And often, we strongly recommend to customers to take advantage of this by spreading your applications across availability zones. And the recommendation is no different for Fargate. We recommend that you create subnets in the different availability zones within a region and pass those subnets into the RunTask API. And the default behavior of Fargate under the hood is that we will spread all your tasks for a given task definition or a service evenly across the availability zones for you. And the idea is that if one availability zone is experiencing problems, some percentage of your application is still up and taking traffic. So that's what we ask you to do to basically design for high availability in your application. But what do we do to make sure that these zones are failing independently? So far, we just have a single stack for the entire region. So let's go through each of these components in our stack to see how we can make them more resilient to single zone failures. So the front-end service. The front-end service, like I said, it hosts the public endpoint that you hit. And that public endpoint is a regional endpoint. So we can't really split the front-end service into zonal services. The cluster manager service keeps state about your clusters. And again, a cluster is a regional construct because you can launch tasks from different availability zones into the same cluster. And also, the zone spread logic that we talked about, that logic actually lives in the cluster manager service. So we can't really split this service into zonal services either. They're logically regional services, but what we do is that the physical servers underneath these services are still striped across the different availability zones. Now let's look at the back half of the architecture. The VPC with the EC2 instances, that has a slightly different story because with EC2 instances, there's nothing cross-zonal about them. An instance is launched in a zone, and everything about that instance, its network interface, its volumes, everything lives within a zone. And the capacity manager is a service that deals with instances, so that's also entirely zonal, and it doesn't perform any cross-zone functionality. So what we can do here is we actually split this part of the stack into separate zonal services. So we actually run a separate dedicated VPC for every zone, and there's a dedicated capacity manager service that's maintaining state about those instances. So the cluster manager service does zone spread logic, picks a zone, and it calls out to the capacity manager service in that zone. So now if there's a problem in a single zone, the regional services may be operating at slightly lower capacity because they've lost a percentage of their fleet, but we make sure that those services are scaled up enough to function without any disruption as far as customers are concerned, even in the face of a zone failure. And on the Dataplane side, we obviously may not be able to launch your tasks into the zone that's having problems, but the other zones are basically functioning at 100% functionality and capacity. So now let's zoom in one more level and take a look at the scaling story within one of these zonal VPCs. So the thing about zones is that we actually don't control how large a zone can get. And by large, I mean how many tasks and thus instances we need to run in a single VPC. And that's because it depends entirely on the distribution of subnets that we're getting in the RunTask API call and sort of the zones that those subnets live in. So because we can't control how large a zone can get, we can't really rely on the fact that a single VPC is able to scale and handle that load. So what do we do about that? So what if instead of having a single VPC for the entire zone, we split it into multiple smaller VPCs? And the thing about these VPCs is that we make them a fixed maximum size. And this is a size that we've tried and tested, and we know that it's something a VPC can handle load-wise. And if we ever happen to fill up the fixed size VPCs that we have here, then we just scale out and add more VPCs. So this is the concept of cellular architecture, where you want to have fixed size units that you understand the scaling characteristics of and scale them out horizontally rather than having a single large unit and try to scale it up vertically forever. And if you have zones that are smaller, then you just have fewer cells in that zone. And in fact, this happens quite a lot. Our zones are pretty imbalanced, especially in regions where we've launched new zones later on. And the added benefit of cellular architecture is that we now get a sub-zonal failure domain here. If something goes wrong at that VPC level, it's only the instances that are running within that VPC will be affected. So putting all of that together, this is what the architecture ends up looking like with our multiple cells for the Fargate VPC. And I want to take a minute to go back to that cluster manager service. That's still a pretty big, important service in our stack, and it's keeping state. It has a database. And it's a little bit of an eyesore that we still have a single box there for the entire region. So what we did is that we applied cellular architecture to the actual service and its database. So we actually run multiple copies of the cluster manager service, and each cellular cluster manager service is responsible for a subset of the clusters. So again, this was done in an effort to reduce blast radius. So that is basically what the entire stack looks like, the Fargate stack looks like. And this is just for one region. And Fargate is now available in all commercial regions. I think that's 22 regions. So we run this entire thing times 22 regions times 60-something zones. So I just want to make the point that we actually go through a lot of trouble and we take on a lot of extra work just to make sure that the service is operating reliably for all of you. And now I want to introduce Firecracker to see how Firecracker can help with scalability. So like I said, Firecracker is new virtualization technology that was developed and open sourced by Amazon, and it's custom built for containers and functions. So how is Firecracker different from other virtualization technologies out there? So if you think of virtualization as a spectrum where you have virtual machines on one end and you have containers on the other end, there's always been this difficult trade-off between security and isolation properties versus startup time. So with traditional virtual machines, you get a rock-solid, hardened isolation boundary between neighboring VMs, but you are booting a full virtual machine, and that often can take long. Whereas with containers, you get lightning-fast startup times because they're just processes, basically. But the isolation boundary between neighboring containers is not quite as trustworthy. So with Firecracker, we think we've hit that right sweet spot on that spectrum where we can get the strong isolation properties akin to traditional virtual machines, but we also get the fast startup times like containers. And Onur will tell you more about how that's possible, but for now, let's see how this works. So with Firecracker, you take a bare metal server, and you basically install Firecracker as the hypervisor, and then you can launch your container workloads inside what we call a micro VM. And as I mentioned before, these micro VMs have strong isolation properties like regular virtual machines, so we can actually co-locate multiple micro VMs running different tasks across customers even on a single bare metal machine. So how does that property help with scalability? In our previous EC2 instance model, we run these EC2 instances in a single tenant manner, meaning that we only ever put one task on an EC2 instance. And like I said earlier, we see tens of millions of task launches a week. And what happens in the single tenant EC2 model is that these tens of millions of task launches get translated one-on-one to tens of millions of EC2 launches, instance launches. And VMs are really heavy, and they're not designed to handle this kind of churn. So it really puts a lot of pressure over there. With Firecracker, what we do is we run EC2 bare metal instances, and we run your task inside of a Firecracker micro VM. And like we said before, we can actually put multiple micro VMs and multiple tasks on a single bare metal instance. So now if we bombard this model with tens of millions of Fargate task launches, it turns into tens of millions of micro VM launches, but micro VM launches, like we said, are designed from the ground up to handle this kind of container-like usage patterns, which are often short-lived and high-churn type patterns. And we only have to launch that EC2 bare metal instance when our existing fleet of bare metal instances are full. So it's a much lower rate of call to the EC2 run bare metal instance API. So we're basically funneling down our calls, and that has really helped reduce pressure, and it just makes it a more tenable scalability story for us. And even if you just remove all the tasks from this picture and just look at the instance density and footprint in these two pictures, the single tenant model versus the multi-tenant model, you can see how our single tenant model is so much denser in terms of the number of instances we're running. And if we think of our fixed size cell again, where we can only put a fixed number of EC2 instances, we get a lot more task mileage from that single fixed size cell with our bare metal model than with our single tenant EC2 model. So that's all I had availability-wise, and now I will hand it over to Onur to cover the rest.
Hello, my name is Onur Filiz, and I'm a principal software engineer working on AWS Fargate. At AWS, security is always our first priority. So let's talk about how we achieve task security and isolation in Fargate. As Archana explained a few minutes ago, today your Fargate tasks run on our fleet of EC2 instances. In this slide, I'd like to walk you through our Dataplane stack to see how we achieve task security and isolation in Fargate. At the bottom of the stack, we have the physical server and hypervisor. The EC2 hypervisor ensures that instances running on the same physical server are isolated from each other using trusted hardware virtualization. Moving up, within our EC2 instance, we run our guest OS, that's Amazon Linux 2, our Fargate agent, and container runtime. Your Fargate task, composed of one or more containers, is running on top of this stack. Now, the container isolation boundary is composed of abstractions like C groups, namespaces, and seccomp policies. Although they provide some level of isolation, at AWS, we do not trust these to be secure enough for multi-tenancy. And so therefore, Fargate never co-locates two tasks on the same EC2 instance, even if they are coming from the same customer. Each instance runs only one and only one task. Once the task completes, the instance is thrown away. It's never reused again. What that means is every time you call RunTask, you get a fresh, new, trusted EC2 instance. This is in order for us to provide you our task-level isolation guarantee. Many of our customers, including financial institutions, have built their own multi-tenant safe applications and platforms on top of Fargate. Okay, so we've said that the EC2 instance boundary is trusted because of hardware virtualization, but the container boundary is not. As a defense in depth exercise, let's go through what would happen if a container were to break out of a task and try to reach other resources on the system. So we said we will never co-locate two tasks on the same EC2 instance, so a task can't locally reach into another task, but what else can it reach? What other components do we have to secure in order to give you our task isolation guarantee? First, there is the guest OS, Fargate agent, and container runtime. Although all these components are reachable from that container, none of them contain any state other than the state for the locally running task. So even if those components are compromised, there is no information there for an attacker to use. But notice also we have the Fargate ANI attached to the EC2 instance. Through that ANI, the task can reach into the Fargate VPC, which runs our other EC2 instances and tasks. And it can also reach into our control plane, which stores our state about other tasks. So that means we have to secure the Fargate VPC and control plane and make sure they are multi-tenant safe. So how do we achieve that? We use the tools and principles that are often recommended to you customers as security best practices. For instance-to-instance traffic inside the Fargate VPC, we make sure all Fargate ENIs are associated with a security group that disallows any communication between instances. We also use VPC flow logs to make sure and monitor that there are no suspicious traffic going on in the Fargate VPC. And for the instance to control plane, the permissions available to the Fargate agent are scoped down to only describe and mutate the state of the locally running task. So even if through a combination of other attack vectors, an attacker gets access to a task ID, it still doesn't have any permission to make any API calls to our control plane. It's all locked down. So now here comes the exciting part. We'd like to show you the new Firecracker-based Dataplane. This is not in production yet, but it's coming soon. Before we do that, though, let's revisit Firecracker to see how it improves our security posture. We said with Firecracker, we can put multiple tasks on the same EC2 instance. Why is that? Firecracker is a virtual machine monitor that is based on KVM. KVM is the same hypervisor that our EC2 instance, the EC2 Nitro platform, is using today. With Firecracker, we can run containers as micro VMs and get the best of both worlds. Just like traditional containers, with Firecracker micro VMs, you get the minimal overhead and fast startup times. However, unlike traditional containers, Firecracker micro VMs also provide an additional layer of trusted security isolation by hardware virtualization. So this is the new Firecracker-based Fargate Dataplane. Let us take a closer look now. So just like our EC2-based Dataplane, at the very bottom we have the physical server that is managed by EC2. Fargate tasks run on our fleet of EC2 bare metal instances. And within the bare metal instance, we run our host OS, again, Amazon Linux 2. and we run our multi-tenant Fargate agent on it. We also run our container runtime, containerd, and our plugin to it, Firecracker containerd. So the Firecracker containerd plugin allows us to run containers as micro VMs. We install the Firecracker VMM, which spins up Firecracker micro VMs. And within the Firecracker micro VM is the guest OS. That OS is dedicated to your task. It's not shared by other tasks. So Fargate team owns and manages all these layers from the host OS on the bare metal instance to the guest OS inside the Firecracker micro VM. That means you don't have to care about the undifferentiated heavy lifting, and you can focus on your applications. Your containers run within the safe environment in user space. As with our current EC2-based Dataplane, your tasks still get their own dedicated ENI. That ENI is only accessible from your task. The Fargate ENI this time remains on the bare metal instance. Okay, so now that we understand the layout of the Firecracker-based Dataplane, let's go through the same exercise that we did before, a few minutes ago, with EC2 Dataplane, and compare them. So as we discussed earlier, the Firecracker micro VM is hardware virtualized and offers a trusted isolation boundary. Firecracker not only isolates micro VMs from each other, but it also isolates micro VMs from the underlying bare metal instance. However, the task and container boundaries are still considered insecure. So repeating the same exercise as before, let's examine the extent of a reach in the case of a container breakout. As you can see, the local guest environment is still within reach, but much of the Fargate Dataplane is now below the trusted line. This is protected by, again, hardened hardware virtualization. So with Firecracker, we were able to greatly reduce the area of attack surface exposed to the tasks, and thus further simplify and strengthen our isolation story. Now let's look at our third and final tenet, that's improving operational efficiency. Fargate offers a wide variety of about 50 different CPU and memory configurations for your tasks. In this slide, we are considering only three of them for simplification. In our EC2-based Dataplane, we run a variety of different EC2 instance types in an effort to best match the task configurations that we offer. However, EC2 instance configurations are a bit more coarse-grained than task configurations, which means there's always some waste inside the EC2 instance, which decreases our utilization. Also, as Archana mentioned earlier, behind the scenes, we run a fleet of EC2 instances. That's because most container workloads expect fast startup times, and having those instances ready and booted up helps with that. However, it also introduces a new type of inefficiency. That is, some of those EC2 instances are now running idle before you call RunTask. Now let us consider the case when there's a burst of small task sizes, and it just fills up our warm pool buffers. With the next request, we can either choose to put that task in a larger instance type, which creates even more waste and therefore reduces our utilization, or we could choose to reject it, but that will reduce our availability. In either case, it's not a good choice to make. Let's revisit Firecracker to see how it helps with this utilization problem. So in addition to the isolation benefits that we discussed earlier, Firecracker also provides two more attributes that is really attractive for serverless platforms like Fargate and Lambda. First, the micro VMs spun up by Firecracker are not traditional VMs, because we made an opinionated choice to emulate a very minimal device model. Most cloud-native workloads do not care about traditional devices in the VM. So stripping them out gives us both very fast startup times. Firecracker micro VMs can start running in a matter of milliseconds. And it also reduces our surface attack area. This is super relevant, again, for services like Fargate, because it means we can launch a Firecracker micro VM on demand when you call RunTask. The second property that is very useful for Fargate is the flexibility and configurability of resources for Firecracker micro VMs. With Firecracker, we no longer have to be bound to the static EC2 instance type and sizes. We can create any micro VM with any CPU and memory size. So when you call RunTask and give us the exact CPU and memory you want for your containers, we can create a new Firecracker micro VM just in time. We call this right sizing. Right sizing enables us to eliminate on-instance waste. And so what this means is that in our Firecracker data plane, we no longer run a heterogeneous fleet of different EC2 instance types. Rather, we run a homogeneous fleet of bare metal instances, which reduces our operational complexity and increases utilization. So as task launches flow in, we are able to configure and launch a right-sized micro VM in milliseconds. This has allowed us to reduce the on-instance and warm pool waste, which in turn allowed us to drop prices earlier this year. Of course, the packing isn't always perfect, so there is some on-instance waste still, but we're still doing way, way better. Another area of innovation enabled by Firecracker is the reduction of the data plane overhead. With the single-tenant EC2 instances, we were first forced to run a copy of the Fargate agent next to each task. So Fargate agent is just another process which consumes CPU cycles and some memory. It's not much, but when you run a large fleet like we do, it does add up. Also, because the Fargate agent needs to talk to the Fargate data control plane, we have to attach a Fargate ENI to each instance. This creates some pressure on our VPCs. Now, comparing that to the multi-tenant bare metal instance fleet, we now run only a single copy of the multi-tenant Fargate agent on the bare metal instance itself. This greatly reduces the waste. Also, now that we have only one copy of the agent, we now only need one Fargate ENI, and that ENI remains on the bare metal instance. So let's review what we've discussed today. Today, we've taken a look at what's under the hood of Fargate. Security of your workloads is always our primary tenet. It's the basis of everything else we do. Next comes availability and reliability. The Fargate team goes to great lengths to ensure that our services remain reliable and secure so that your tasks run safely. And finally, we will keep innovating to improve our efficiency. Efficiency enables us to provide you better performance using less resources, which reduces our costs, which means you get to enjoy more price reductions. AWS Container Services team is here in reInvent. We have many related breakouts and sessions. This is a list of some of them. You can choose to attend them here or watch the videos later on YouTube. We also have a public roadmap on GitHub. This is where you can learn about upcoming features, file issues, create feature requests, and ask questions to the actual team members who are building them. We want to hear your opinions. We hope you found this session useful. So on behalf of the Fargate team, we'd like to thank you for your time. And now I think we'll have some time for questions. Thank you.